Okay, so I'm going to turn it over to Derek and YangQuan, who are going to talk about methane emission drone swarm sensing to better understand permafrost thawing dynamics. So take it away.
Awesome, thank you. So the main goal of this talk is to sort of give you a brief overview and try to make the point that why we need swarm sensing to understand this problem. Next slide, please. And so the question becomes, so what and who cares? And so methane in general is more than 25 times more potent than CO2 at trapping this heat in the atmosphere as global warming. And it contributes as a positive feedback actor. So in control theory, this is bad. One of these feedbacks could be from the permafrost, which is mainly frozen soil that contains a lot of carbon. And as it thaws, it can release the methane and CO2. And so there's some other natural resources that suspected to have releases like this, other emissions, such as wetlands or vernal pools, such as the image in the upper right, or from anthropogenic sources, from oil and gas industry, such as the PG&E testing facility we flew at in the bottom left, or in agriculture in general, which could come from cattle or other crops where they tried to collect and anaerobically digest and collect the gas and turn it into heat and electricity. Next slide. And so although this plays a big role in the global carbon cycle, there's a lot of uncertainty regarding these emissions. This is true for both anthropogenic and natural resources. And typically because natural resources are so low, the source emission rate, they're both hard to detect and quantify. And this can lead to other hazards such as extreme weather events or such as this San Bruno incident, which resulted in an explosion from a gas leak that went undetected. And some of the current technology using right now is like through remote sensing small aircraft. So the image on the upper right is from Avaris NG, where it shows a 25 meter squared pixel resolution of a geological natural source. So we may still be missing information there, which is why we need a better resolution. Other instruments such as the eddy covariance tower or chambers have been used, which is in the bottom right. And those are typically expensive. They require power to operate, and there's usually one per site, which makes it very difficult to scale up regionally to answer the big picture question. Next slide, please. And so it wasn't until recently that NASA JPL had taken some of the instruments they developed for the rover and miniaturized it down into an instrument that we can then use onboard a drone that has very good sensing capabilities. So resolution or sensitivity down to about 10 parts per billion, which is 2 orders of magnitude better than other instruments, as well as rapid sampling rates, such as 5 Hertz. And when we applied this to the Alaska peatland experiment, which is the image shown in the right, we can fly these upwind and downwind curtains, which are basically the raster scanning vertically. We can measure the emissions coming from these sites. Although the downside is that we depend on the atmosphere to be very stable and doesn't change. And this is not the case. It never really behaves well. The next slide, please. And so this presents a new framework that we are considering is by using things such as centroidal Voronoi tessellations, which is essentially a way that we can do formation control with drones. We can create these curtains to measure the upwind and downwind emissions from the site, where we don't have these spatial temporal issues that you would by doing the original curtains through the raster scanning. And this can include doing control for the angle of this plane in respect to the wind and source direction, as well as introducing physics-informed approaches into the mathematics. Next slide, please. And so this cannot be tested, at least in simulation, by improving models such as digital twins. And so this allows us to have an acceptable level of fidelity with the simulation, but allowing us to understand and predict and optimize performance of the swarm strategy, as well as introduce control concepts such as modeling, analysis, and design, so we can close the loop and reiterate. And so I'm just showing you a few slides here, but the conclusion is that using this approach will allow us to better understand permafrost thawing dynamics when we apply it in the field. And that's all I have. Thank you.